Hey everyone, welcome to this explainer brought to you by Forge College. So, if you joined us for the last lesson, we walked through some beautifully automated AI-assisted refactorings for our program entry points. Everything looks clean, totally organized, and running super efficiently, right? Well, today, we're shifting gears a bit. We're moving from just making our code look good to making it absolutely bulletproof. Today's focus is all about security and debugging strategies for those entry points.
Okay, let's dive right into this, because honestly, out in the wild of Web3, even the most beautifully refactored code is completely exposed to real-world threats, and one of the biggest vulnerabilities you're going to face is account tampering. Just imagine someone strolling up to a bank teller and handing them a totally fake ID to try and access a vault. If your program's entry point doesn't explicitly check that ID, well, it's just going to let them right in. So our goal today is to understand exactly how to test for these failure modes and stop them dead in their tracks.
Now, you might be wondering how this works with larger interactions. Well, one of the absolute most powerful, but also kind of tricky features of building on Solana is the cross-program-invocation, or CPI for short. A CPI is really just one program interacting with or invoking another program directly. It's a lot like delegating a task to a completely different department. But here's the catch. When CPIs happen, all of your standard entry point assumptions change. You just can no longer blindly trust the data coming in because it's being handed off from an external source. And that means we need specific, highly targeted fortification right at the front door.
So, before you ever allow a state mutation, I mean literally before you change any data, update any records, or move any assets at all, you absolutely must run through a concrete set of checks. First up is account validation. This means verifying exact public keys and ensuring the right signers are actually present. Second, the instruction-discriminator. You need to verify that the 8-byte hash of the requested instruction perfectly matches your specific program logic. And finally, you have to catch errors like not enough account keys if a user forgets to provide the full context. If literally any of these fail, the transaction has to halt immediately, no exceptions.
Right, so knowing the checks is one thing, but how do we actually guarantee they work? Well, we build a small test harness. Think of this process like a senior engineer walking you through a debug report. It's a 3-step flow. Step 1, document the failing input. We intentionally try to tamper with the account and just watch it fail. Step 2, apply the fix. This is where we inject those specific security checks we were just talking about. And Step 3, verify the passing test. We run that same tampering attempt again, and this time, our defensive checks block it perfectly. It is a super clear, totally repeatable loop.
Now, during this whole testing process, visibility is absolutely everything. You need to know exactly why a test failed or why it passed. And that brings us to a really vital checkpoint, using the MSG macro. Think of the MSG macro as your own personal magnifying glass into the blockchain's execution logs. By strategically placing these messages in your code, you can verify that your entry-level checks are actively catching malformed inputs. Because, it's not enough to just see a failure. You want the log to explicitly tell you that your specific security checks actually prevented unsafe behavior.
So what does this all mean for us? The crucial takeaway here is this. By combining concrete security checks with a really solid test-driven debugging flow, we achieve our main objective, which is hardened entry points. And why is it so incredibly important to get this done right now? Because it ensures absolute robustness. You really cannot integrate fragile programs into larger workflows or, say, your final capstone project. You have to know for sure that the front door is locked tight so the rest of your program's logic can operate safely behind it.
Which actually leads us perfectly into what comes next. In our next lesson, designing a robust program entry point, we are going to take all these defensive checks and testing strategies and convert them into a durable design pattern that you can reuse across literally every program you write. But before we wrap up today, I want to leave you with a quick thought. If your program's entry point is the single gateway between the outside world and your code's internal logic, how confident are you in the locks you're building today? Keep that in the back of your mind as you practice. Thank you so much for joining this explainer, created by Forge College. Be sure to head over to forge.college to learn more about Web3 and keep leveling up your skills. Catch you in the next one.